My dear students, in the last class, we have understood the various concepts of an reinforced cement concrete and why a reinforced cement concrete we understood, and also later we understood the various methods of analysis, that is working stress method, ultimate load method and limit state method. And we understood the various partial safety factors why it has to be used. So today we shall try to understand the concepts of mechanics of reinforced cement concrete members to do the derivations for limit state method. Now coming to this reinforced cement concrete, as we understood that we are using two materials, hence we call it as a composite action. So here the reinforcement this is called the reinforcement and this is the concrete. So here this reinforcement as well as the concrete will undergo the same strain or deformation as the surrounding to prevent the discontinuity or a slip. That's why we use both the materials here. And the direct stress is transferred by the concrete to the bar interface so as to change the tensile stress and reinforcing bar along its length. So this is called as a mechanics of the reinforced cement concrete member. So hence concrete reduces the compressive stress, steel reduces the tensile stress. So here is a loading frame where we observe the longitudinal beams, transverse beams, this is called as a longitudinal beams, this is called as a transverse beam, the slab panel, and then goes to the column and the foundation here. So with this, let us try to understand the concept of how does an RCC beam will behave. Basically, all these beams are called as flexural members. Flexural members means the bending members. Whether it is a slab or a simply support beam, it will bend into an arc of a circle. So hence, now, as we understood in the last class that we have working stress method, ultimate load method, and later we came to limit state method. So hence, as we found that limit state method has a quite advantages, now we shall understand how does this design goes with limit state method. Now we are seeing as a beam here. Now the beam is bending an arc of a circle here. The bottom is subjected to tensile and the top is subject to compression. So hence we have something called as a flexural failure in the middle of this. Like that, we may have a diagonal cracks coming here that is called as shade cracks. So hence we should provide the flexural reinforcement to prevent the flexural cracks. Like that, to prevent the shade cracks, we have to provide the shade reinforcement. One by one, we shall understand the concept. Hence, the longitudinal bars which will be put in the beam here, that is called as to reduce the tension forces due to the bending, while the vertical stirrups to reduce the shade cracks. So that's what this is the shade reinforcement, what you see here. Such a stirrup is called as an two-legged stirrup because I have one leg here, two leg, that's what is called as a two-legged stirrup, and this is called as a longitudinal bar. So here is a pictorial representation of a cross section of a beam here. So hence this longitudinal bar should be of a heavier diameter, whereas the shade reinforcement should be of a smaller diameter and put into closed loops here. So with this small pictorial representation of a beam, what it has a longitudinal reinforcement and a lateral reinforcement. We call this lateral reinforcement as stirrups. So now we shall try to understand what is meant by limit state of collapse flexural beams, which is told in the page number 67 of IS 456 2000. So please take out IS 456 page number 67, and now we shall try to understand whenever beam is cross section is here, flexural cracks occur in the directly like this. These cracks are called as shade crack pattern. So this are again we have a crack pattern of various researchers done. Shade cracks are observed here. All the diagonal cracks are called as shade cracks. The fractional failure in a tension occurs due to the strains in the compression stress as the beam approaches failure in the tension. Similar way, when you please take out page number 69 of IS 456. Now whenever we want to do a derivations, we have to understand, we have to assume some assumptions. Just like in strength of materials, we assume in plane sections before bending it will remain plane, after bending stress is proportional strain. Like that, we have assumed the assumptions may reinforce cement concrete member. So hence, please take out page number 69 of IS 456 where already the same data is there. Now what is the first assumption? Plane section normal to the axis remain plane after bending. The same assumption we have stated or you have understood in the third semester strength of materials with respect to beams as well as done the columns. Same way, the second assumption is, why this assumption is to be taken? Ensure that the cross-sectional member does not wrap due to the loads applied. It further means the strain at any point of the cross-section is directly proportional to the distance from the neutral axis. So this is the meaning of the assumption what you learned in third semester. I'm giving a brief explanation of this assumption. The second assumption tells that, please refer page number 69 once again. The maximum strain in the concrete, the outermost compression fiber, is assumed as 0.0035 in bending. The explanation is here like this. It is very clear that the specified limiting strain 0.0035 does not depend upon the strength of the concrete. The acceptable stress strain curve as per page number 69. In figure number 21, it tells that it is a parabolic. That means to say at no load you have zero stress and zero strain. Then it is a parabolic curve till an initial strain of 0.003 and the final strain is 0.0035, which is in the concrete. This is called as the FCK grade of concrete, and the design stress of the concrete is 0.67 FCK. And now this chart or graph is there in page number 69 of IS 456 2000. So now this is called as a characteristic compressive strength of the concrete. So hence in the page number 68 we have discussed in the last class that design strength of the material is equal to characteristic strength divided by partial safety factor, hence 0.67 FCK by gamma m. And in the last class we have understood gamma m for the concrete should be taken as 1.5. So hence when I substitute 0.67 FCK gamma 1 as 1.5, I get 0.446 FCK. So please keep in mind this I'll be using later. So hence the design compressive stress strain is obtained by reducing the values top parabolic curve in two stages. First dividing by 1.5 to the side effect and then gamma m. The middle and bottom curves represent these stages. Thus, the maximum compressive stress in bending is 0.446 of FCK. And how do I get 0.446 of FCK? So please go back to the slide. 0.67 gamma m is 1.5. 0.67 divided by 1.5 will give you the 0.446 of FCK. So now, as per page number 70 or 69 of IS 456, the tensile strength of concrete is to be ignored, because entire concrete section is assumed to be cracked in tension zone. Hence, the entire tensile force is considered by steel only. Hence, the tensile strength of concrete to be ignored. So this is the fifth one. What we have, design stresses of the reinforcement are derived from the stress strain curve of page number 69, where partial safety factor for steel is taken as 1.15. So hence, sixth assumption is maximum strain, the tension reinforcement in the section, the failure shall not be less than. This also as given in the page number 70 of IS 456, where Young's model of steel is 2 into 10 raised to 5 Newton per mm square or 20,000 megapascal. This assumption ensures that ductile failure in which the tensile reinforcement undergoes a certain degree of inelastic deformation before concrete fails in compression. So hence, today we shall try to understand the types of RCC beams, the area of tension reinforcement, at failure if the concrete is maximum 0.035, the maximum is as per the equation given, that is Fy by 1.15 plus 0.002. So maximum tension, the strain in the concrete is so much, and this is the maximum strain in the steel. Hence, if the steel has attained less strain than the maximum strain, then we call it as an under reinforced section. If the strain in the steel is what is to be adapted and what I get, then such a beam is called as an balanced section. If the strain in the steel is less and concrete has attained more, such a beam is called as an over-reinforced beam. In the next class, I shall be explaining you the various kinds of derivations of an under-reinforced beam, balanced section as well as over-reinforced section. So this also I shall be talking later. Now, we shall try to understand, we end up this class with analysis. What is meant by single reinforced beam? If I provide the reinforcement only in the tension zone, is called as a single reinforced beam. So this is what two-point loading, where you draw the bending moment diagram. From here to here, you have a constant bending moment, but the shear force will be 0. So hence in this class, we shall talk about the derivation of this. So today we have understood only the what is meant by an under-reinforced beam, balanced section, as well as an over-reinforced sections. And also we have understood the various assumptions which might be asked examinations for 6 marks. Please copy the page number 67 and write down 69, from the referring the code book. So I shall end up the class today. So have a goodbye.